Okay, let's have another look at some examples then for force, work and power. So let's imagine we have our brick here. Let's say the brick has a mass of 2 kilograms and it's on the table. There's the table. Let's imagine we put it on a little pulley. There's our pulley, and we're going to pull that up. Let's say we're going to pull that up to 7 meters. So the brick's going to end up here when we pull that up. Well, we need to work out the force of the brick pushing down on the table. F equals mass times acceleration equals 2 times 9.81. 2 times 9.81. 19.62. Now force is measured in newtons, so that is newtons. If I now pull this rope and lift the brick up 7 meters, that's going to use some energy. So the work done equals force times distance. So that becomes the force, 19.62, times 7 meters. So multiply that, I've left that on the display, times 7 equals 137.34 joules. That's work done. Now I've got to say, well, how fast do I want this to go up in the air? Well, let's say we did it in 3 seconds. Lift in 3 seconds. What power is required to do that? Well, power equals work divided by time equals 137.34 divided by, let's say we did that in 5 seconds. So I've left that on the display. Divide that by 5 is 27.46. So that becomes 27.46 watts. Okay. So if I wanted to order a motor to do that work, I'd need to get one that can be powerful enough to produce that lift in with 27.46 watts. So you need a motor rated over 27 watts to do that job, if you wanted that. Okay. I'm getting on for time, 5 minutes. Right, let's have another look at a bit more practical situation. Let's imagine we have a lift car here, and there's our motor room up here. Let's imagine this building is, say, the lift has to go up, say, to 85 meters. Let's say the lift car weighs, I don't know, let's say 300 kilograms. So what you have normally is a counterbalance in a lift shaft which weighs the same as the lift car, so they cancel each other out. So all you're worried about really is the people standing inside. Right. So let's imagine that 3 people are in there and each of them weighs 75 kilograms. So the load is 3 times 75. 225 kilograms. So as soon as they get in the lift, the force pulling down on this rope is an extra mass times acceleration equals 225 times 9.81. And that comes to 2,207 newtons. That's got to be lifted 85 meters. So the work done, force times distance, equals 2207 times 85, and that comes to 187,616 joules. So the power required, well, if you're designing your lift for your building, you need to decide how fast this lift is going to go. So you might expect the lift to travel up 85 meters in, say, 30 seconds. So you say power required for 30 seconds lift. Power equals work divided by time equals 187,616 divided by, we want it done in 30 seconds. So I divide that, I've already still got it on my display there, I divide that by 30, I get 6,253. 6,253 watts, which is about 6.3 kilowatts. So the motor here needs to be at least probably around 7 kilowatts to power that lift to get it 85 meters in 30 seconds. Okay, so with these questions we're usually after three things. We're after the force required, the amount of work done, and the power required to lift it in a certain time. Okay, so I'll put some more examples like that on solar. Thanks, bye now.